a logarithmic function? Well, if f of x, if L is to be a logarithmic function, if b is any constant, in particular, L of b times x had better be equal to L of b plus L of x. That's the definition of logarithmic. Now, we don't know if that's true. What do we have at our disposal to be able to see whether we can solve this problem or not? How do we, using calculus, check to see whether two functions are equal? Remember, the standard approach is what? Take the derivative of both sides. If the derivatives are equal, then the functions differ by a constant. And if we can show that that constant is 0, then the two functions are equal. So let's take a look and see how that works over here. First of all, let's see what the derivative of L of bx is with respect to x. And by the way, here again is the beauty of what we mean when we say that all of the study that we're making allows us to utilize every fundamental result that we've learned before. We've learned that the basic definition of L is what? That if you differentiate L with respect to the given variable, you get 1 over that variable. We want a derivative of L of bx with respect to x. Now, you see, the idea is the derivative of L of u with respect to u is 1 over u. You see, by the chain rule, if we were differentiating L of bx with respect to bx, that would be 1 over bx. I shouldn't say by the chain rule yet. What I'm saying is, if we differentiate L of bx with respect to bx, we would have 1 over bx. But we're not differentiating with respect to bx, we're differentiating with respect to x. And this is where the chain rule comes in. Namely, we rewrite the derivative of L of bx with respect to x as the derivative L of bx with respect to bx times the derivative of bx with respect to b. And in this way we get what? The first factor is 1 over bx. The second factor is b itself. Remember, b is a constant. And therefore, the derivative of L of bx is 1 over x. On the other hand, what is the derivative of L of b plus L of x? Since b is a constant, the derivative of L of b is 0. And by definition, the derivative of L of x with respect to x is 1 over x. And now you see, comparing these two results, we see that L of bx and L of b plus L of x have the same derivative. Hence, they differ by a constant, which I'll call c. In other words, notice that capital L is what I call almost logarithmic. If it weren't for this fact, this constant c in here, it would be a logarithmic function. Well, at any rate, what do we have? We know that capital L of bx is equal to capital L of b plus capital L of x plus some constant c. To evaluate the constant, we only have to evaluate it at one element in the domain. Let's pick x equal to 1. The motif being that if x is 1, notice that on the left-hand side you have an L of b term, on the right-hand side you have an L of b term, and they will cancel. In other words, if x is 1, this equation becomes L of b equals L of b plus L of 1 plus c, from which it follows that c is minus L of 1. C is minus L of 1. Now, what do we want c to be? If c were equal to 0, if c were equal to 0, this would be logarithmic, and all we need to make c equal to 0 is to set L of 1 equal to 0. In other words, summarizing this result, capital L of x is logarithmic if capital L of 1 is 0. Now remember, we have a whole family of L's that work. What we're saying now is, let's pick the member of the family of L's that passes through the point 1, 0, and because that's logarithmic, let's give that a special name. In essence, we will define this symbol. It's written Ln of x. It will later be called the natural logarithm of x. I'm trying to avoid the word logarithm here as much as possible because I want you to see that we haven't had to use exponents at all in making this kind of a definition. But let's define Ln of x to be the member of the family capital L of x plus c, which passes through the point 1, 0. In essence, then, what is Ln of x? I'll call it natural log. It's easier for me to say. The natural log of x is that function whose derivative with respect to x is 1 over x, and characterized by the fact that what? If the input is 1, the output is 0. In other words, the graph passes through the point 1, 0. Again, notice that In terms of what we said earlier in today's lesson, we talked about the functions L of x and talked about, in the differential calculus approach, the curve could go through any point on the x-axis. What we're saying is now, if the point on the x-axis that the curve crosses at is 1, 0, that's what ln x will mean, the natural log function. In terms of the integral calculus approach, if the particular a value that we choose, the fixed value that we're going to study the area under, notice that all we're saying is pick a to be 1. And by the way, as a quick check, all we're saying is what? The natural log of x is defined to be the area under this curve as a function of x. In terms of the definite integral, that's the integral from 1 to x dt over t. And notice that if you pick x to be 1, the natural log of 1 is the integral from 1 to 1 dt over t, and that's 0, just as it should be. Okay? So at any rate now, that tells me how to define the natural log. Am I doing this in terms of exponents? No. I am trying to do what? Find a function whose derivative with respect to x is 1 over x. And I would also like that function, since it's that close to being a logarithmic function, to be a logarithmic function. In other words, this is how I invented the function ln of x. The natural log of x, its derivative with respect to x is 1 over x, and the natural log of a product is the sum of